Welcome to Sleepy Earth channel. Tonight, we're traveling back to a forgotten version of Earth, a world before forests, before dinosaurs, and before humans ever existed, where giant mysterious towers may have ruled the planet. Together, we'll explore the strange age of colossal fungi, alien landscapes, and the hidden ecosystems that shaped life on Earth long before history began. Before we begin, leave a comment telling me what city you're watching from tonight. And let's slowly drift into this ancient lost world together. More than 400 million years ago, Earth did not look like the world you know tonight. There were no forests whispering in the wind, no birds crossing the sky, no grasslands, no flowers, and no ancient kingdoms waiting somewhere beyond the horizon. In fact, if you had somehow stood on the surface of the planet during that distant time, you might not have even recognized it as Earth at all. The continents were barren and strangely silent. Vast stretches of rock extended beneath a dimmer sun, interrupted only by shallow wetlands, dark microbial mats, and low clusters of primitive plants barely tall enough to reach your ankles. The air itself carried a different chemistry. Oxygen levels were lower than today. Carbon dioxide was far higher, and storms rolled across landscapes that had never known human footsteps, animal migrations, or the sound of leaves moving through trees. And yet, rising from this empty, alien world, there stood something enormous. Towering columns as tall as telephone poles appeared across the land long before the first forests ever existed. They looked almost like tree trunks from a distance, but there were no trees yet, no wood, no branches, no roots in the modern sense, just gigantic living structures rising alone from the prehistoric ground, casting shadows across a world still learning how to exist on land. For a very long time, scientists struggled to understand what these things actually were. Some believed they were ancient conifers. Others thought they might be giant algae washed onto shore. A few suspected they represented an entirely extinct branch of life with no modern equivalent. But today, many researchers believe these mysterious giants may have been something far stranger. They may have been colossal fungi, organisms related in some distant and almost unrecognizable way to the mushrooms growing quietly in forests today. Their name is Prototaxites, and for millions of years they may have been the tallest living things on Earth. The idea sounds almost absurd at first. It is difficult for the modern mind to picture a planet ruled not by trees or dinosaurs, but by gigantic fungal towers standing across fog-covered plains. Yet the fossil evidence is real, and the mystery surrounding these organisms has only deepened over time. Some fossil specimens suggest heights reaching more than 8 meters tall and widths over 1 meter thick. In an age when most land plants barely reached knee height, these structures would have dominated the horizon completely. Imagine walking through a prehistoric wetland where the tallest life form on Earth was not a redwood or a pine, but something more closely related to mold. That alone changes the emotional atmosphere of ancient Earth entirely. It transforms the planet from something merely old into something deeply unfamiliar. And perhaps that is what makes this chapter of Earth's history so unsettling and fascinating at the same time. Because when most people imagine prehistoric Earth, they picture dinosaurs immediately. Massive reptiles, volcanic landscapes, giant predators. But the age of dinosaurs would not begin for well over 150 million years after Prototaxites first appeared. These fungal giants belonged to a much older and stranger Earth, one still transitioning from an ocean world into a planet where life could survive on land. At that time, life had only recently begun experimenting with terrestrial existence. Before that transition, most organisms remained confined to the seas. The land itself was hostile. Ultraviolet radiation struck the surface with little protection. Soil barely existed in the modern sense. Nutrients were difficult to retain. Water evaporated quickly from exposed surfaces. Surviving on land required entirely new biological strategies. And strangely enough, fungi may have been among the first organisms capable of truly mastering that challenge. Even today, fungi possess abilities that almost feel unnatural. They can break down rock chemically. They can digest dead material into nutrients. They can spread through microscopic networks underground for astonishing distances. Modern forests depend heavily on fungal systems beneath the soil, invisible networks linking plant roots together in ways scientists are still trying to fully understand. Some researchers even describe fungal systems as a kind of natural communication infrastructure for forests. But hundreds of millions of years ago, before forests existed, those same biological advantages may have allowed fungi to dominate the empty continents themselves. In many ways, fungi were uniquely suited for an unstable prehistoric Earth. They did not need deep soils like trees. They did not depend on complex ecosystems already being established. They thrived in damp, carbon-rich environments. And during the Devonian period, the planet offered exactly those conditions. Atmospheric carbon dioxide was likely several times higher than modern levels, creating a greenhouse climate across much of the world. Rainfall patterns may have been intense in certain regions. Wetlands expanded across low-lying landscapes. Primitive plants slowly spread outward from rivers and coastlines, but they remained small and structurally weak. Without large woody trees competing for sunlight, something like Prototaxites could rise almost uncontested into the prehistoric sky. And yet, the deeper scientists looked into these fossils, the stranger the mystery became. Under microscopic analysis, the internal structure of Prototaxites did not behave exactly like wood. It lacked the organized cellular patterns expected in tree trunks. Instead, many specimens showed tangled, tube-like structures more similar to fungal tissues. Later chemical studies examining carbon isotopes added even more intrigue. Trees and photosynthetic organisms typically produce relatively consistent carbon signatures because they generate energy directly from sunlight. But Prototaxites showed wildly variable carbon isotope values between specimens, suggesting it was not producing its own energy through photosynthesis. Instead, it may have absorbed nutrients from surrounding organic material, like fungi do today. That evidence pushed many scientists toward the fungal interpretation. Still, the debate never completely disappeared. Some researchers argue that Prototaxites may not fit neatly into any modern category. It may have been fungus-like without being a true fungus. Or perhaps it represented a biological experiment from early terrestrial life that no longer exists. The deeper paleontology explores Earth's distant past, the more it becomes clear that evolution was not always moving toward familiar outcomes. Entire forms of life may have flourished for millions of years before vanishing so completely that modern biology struggles to classify them. That possibility gives ancient Earth an almost dreamlike quality, a reminder that the planet once hosted ecosystems with no modern equivalent at all. But perhaps the most haunting part of this story is the atmosphere these organisms existed within. Because this was not merely a world without humans, it was a world before complex terrestrial ecosystems had stabilized. The silence would have felt immense. No birdsong, no mammal calls, no rustling forests, only wind moving across wet stone and primitive vegetation beneath towering fungal structures that may have released clouds of spores into the humid air. Early arthropods crawled across the ground nearby. Millipede-like creatures explored the damp surfaces. Tiny primitive plants clung close to streams and marshes. The continents themselves still looked raw, almost unfinished, as though Earth were in the middle of constructing the ecosystems we now take for granted. And for millions of years, these giant organisms stood at the center of that transformation. In some ways, Prototaxites represents more than just a prehistoric curiosity. It symbolizes a forgotten stage in Earth's development, a period when the rules governing life on land were still uncertain. Today, forests dominate continents so completely that it feels inevitable they always would have. But evolution rarely follows inevitability. If environmental conditions had shifted differently, if certain plant lineages had failed, perhaps fungal ecosystems might have remained dominant much longer. It is entirely possible that Earth's history could have unfolded along radically different biological paths. That realization quietly changes how we see the modern world. Forests, animals, even human civilization begin to feel less permanent and more accidental than they first appear. Because before trees conquered the continents, something else may have ruled the horizon. Something stranger, something modern Earth barely remembers. And perhaps the most fascinating part is this. Despite decades of research, scientists still cannot answer every question surrounding these enormous organisms with certainty. New discoveries continue to reshape interpretations. Some fossil evidence supports the fungal theory strongly. Other details remain difficult to explain completely. Even now, paleontologists continue debating exactly how Prototaxites lived, reproduced, and interacted with its environment. There is something strangely beautiful about that uncertainty. The deeper humanity investigates the ancient world, the more it discovers that Earth's past is not a clean narrative leading predictably toward the present. It is filled with experiments, dead ends, vanished kingdoms of life, and organisms so alien that modern language struggles to describe them properly. Long before the first forests covered the continents, long before dinosaurs walked the earth, and unimaginably long before humans looked up at the stars and wondered where they came from, the planet may have belonged to giant living towers of fungus rising through prehistoric fog beneath an unfamiliar sky. For more than a century and a half, one of the strangest fossils ever discovered has quietly challenged humanity's understanding of early life on Earth. Even now, after decades of modern analysis, scientists still cannot fully agree on what it truly was. Some researchers see evidence of a gigantic fungus unlike anything alive today. Others suspect it may represent a completely extinct form of life that modern biology cannot properly classify anymore. And perhaps the most unsettling possibility is that both ideas are only partially correct. Because the deeper paleontologists investigated the organism known as Prototaxites, the more mysterious it became. The story began in the mid-1800s, long before anyone imagined giant fungi dominating prehistoric landscapes. Fossils of enormous cylindrical structures had been found preserved in ancient rocks dating back hundreds of millions of years. At first glance, they resembled tree trunks. That interpretation seemed obvious. After all, what else could create a long vertical structure several meters tall? The fossils even displayed ring-like internal patterns in some specimens, almost resembling growth rings found in wood. To 19th century scientists trying to reconstruct Earth's distant past, the simplest explanation was that these were remnants of primitive trees belonging to Earth's earliest forests. But there was one enormous problem with that interpretation. The rocks containing Prototaxites fossils were older than the world's first true trees. At the time these organisms existed, complex forests had not fully evolved yet. Most land plants remained small, low to the ground, and structurally fragile. Some barely reached waist height. Yet here were fossilized structures towering far above everything else known from the same ecosystems. It was as if someone had discovered the remains of skyscrapers in a civilization that had not even invented villages yet. The timeline did not make sense, and slowly, the confidence surrounding those early explanations began to fracture. As fossil evidence accumulated, researchers noticed additional inconsistencies. True wood contains highly organized vascular tissue designed to transport water through trunks and branches. Prototaxites lacked those familiar structures. Under closer examination, the interiors appeared composed of tangled microscopic tubes rather than the ordered cellular systems expected in trees. The more carefully scientists studied the fossils, the less they resembled conventional plants at all. By the early 20th century, some paleontologists proposed entirely different ideas. Perhaps these structures were giant algae washed onto land from ancient seas. Others suggested they might have been massive lichens, strange partnerships between fungi and photosynthetic organisms. But no theory completely solved the mystery. Every explanation fit certain details while failing to explain others. And so, Prototaxites drifted into a strange scientific category, famous enough to intrigue researchers, but elusive enough that no consensus fully settled the debate. What makes the mystery especially compelling is the sheer scale involved. Some fossil specimens indicate heights exceeding 8 meters, roughly comparable to a 2-story building. Others suggest widths more than 1 meter across. In today's world, giant mushrooms of that size sound impossible, almost fantasy-like. Modern fungi simply do not grow into towering vertical monuments dominating entire landscapes. Most mushrooms are temporary fruiting bodies emerging briefly from much larger underground networks. But Prototaxites seems to have operated according to rules that no longer exist. It belonged to an Earth with different climates, different ecosystems, and possibly different biological opportunities entirely. During the Devonian period, the continents were still undergoing a transformation unlike anything happening today. Land ecosystems remained relatively open and unstable. There were no dense forests competing aggressively for sunlight yet. Atmospheric chemistry differed dramatically. Soil systems were primitive. Entire ecological niches existed that later disappeared once trees and complex terrestrial ecosystems evolved. In that environment, something as bizarre as a giant fungal tower may not have been impossible at all. In fact, it may have been perfectly adapted for its moment in Earth's history. One of the most important breakthroughs in understanding Prototaxites came much later through chemical analysis rather than visual appearance alone. Scientists began examining carbon isotopes preserved inside fossil samples. This may sound technical at first, but the underlying idea is surprisingly elegant. Organisms interact with carbon differently depending on how they obtain energy. Plants using photosynthesis typically leave behind fairly predictable isotope patterns because they absorb carbon directly from the atmosphere through sunlight-driven processes. Fungi behave differently. Instead of producing their own energy, they absorb nutrients from surrounding organic matter. When researchers analyzed Prototaxites specimens, they discovered something unexpected. Different samples showed wildly inconsistent carbon isotope values. That inconsistency suggested these organisms were not relying on photosynthesis the way plants do. Instead, they appeared to consume external organic material, more consistent with fungal behavior. To many scientists, this evidence became one of the strongest arguments that Prototaxites truly was a fungus, or at least something closely related to fungi. Yet even that conclusion left enormous unanswered questions behind. If Prototaxites was fungal, what exactly was it feeding on? The Devonian world contained far less complex plant material than modern forests. Massive dead logs and thick leaf litter did not yet cover the land. Nutrient sources would have been comparatively limited. Some researchers speculate that Prototaxites may have consumed microbial mats, primitive plants, decaying organic films, or even symbiotic organisms living within its own structure. Others wonder whether it operated through ecological relationships that no longer exist anywhere on Earth today. And that possibility may be the most haunting aspect of the entire mystery. Modern biology tends to categorize life neatly into familiar systems, but early terrestrial ecosystems were experimental in ways difficult to imagine now. Evolution had not settled into stable long-term patterns yet. Entire strategies for survival may have appeared briefly before vanishing forever. Prototaxites could represent one of those lost experiments, a biological architecture Earth tried once and never repeated again. The fossils themselves only deepen that feeling. Some specimens preserve internal tube networks, twisted together in almost chaotic arrangements. Others appear layered or irregular in ways unlike modern tree growth. Certain paleontologists have compared their textures to rolled mats of microscopic filaments compressed over immense spans of time. Looking at cross-sections of Prototaxites does not create the reassuring familiarity of examining wood. Instead, it feels strangely alien, as though the fossil belongs to a world following biological rules only partially connected to modern life. And perhaps that emotional reaction matters more than it first appears. Because paleontology is not merely about identifying ancient organisms. It is also about confronting how unfamiliar Earth once was. Human beings instinctively reconstruct the past using modern analogies. We imagine ancient forests, ancient oceans, ancient animals that resemble today's ecosystems in rough form. But organisms like Prototaxites disrupt that comfort entirely. They suggest that large portions of Earth's history may have looked emotionally and biologically stranger than most people realize. There may have been entire landscapes where the dominant life forms have no real equivalent today. Entire ecosystems whose logic disappeared hundreds of millions of years ago. Some scientists remain cautious about labeling Prototaxites a fungus with complete certainty for exactly that reason. Certain structural details still resist perfect classification. A few researchers argue that it may represent a giant lichen-like organism rather than a pure fungus. Others suspect it occupied an evolutionary branch somewhere between categories we now treat separately. And because soft biological tissues rarely fossilize perfectly, many details may simply be lost forever. Paleontology often works like reconstructing an ancient civilization from scattered ruins buried beneath oceans of time. Every fossil provides clues, but never complete certainty. There is always interpretation involved, always room for competing possibilities. Yet strangely, that uncertainty may be what makes Prototaxites so captivating. In a world where people often expect science to provide immediate, definitive answers, Prototaxites reminds us that some mysteries survive even under intense modern investigation. The fossils have been scanned, sliced, chemically analyzed, debated, and reinterpreted repeatedly for generations. And still, this ancient organism refuses to fit comfortably into a single explanation. It remains partially hidden behind deep time itself, almost like a message arriving from a prehistoric Earth too distant for modern language to fully decode. But perhaps the most astonishing realization comes when imagining how these organisms actually appeared in their living environment. In the modern world, fungi are usually associated with decay, darkness, or hidden underground networks. They are background organisms, quiet recyclers beneath ecosystems dominated visibly by plants and animals. Prototaxites may have represented the complete opposite. It may have stood boldly above the landscape itself, visible for miles across open prehistoric terrain. Massive vertical structures emerging through fog and rain, long before forests transformed the continents. If humans had somehow witnessed that world, they likely would not have interpreted these giants as fungi at all. They would have seemed more like living monuments from another planet, strange towers growing silently beneath a dim, prehistoric sky, while primitive arthropods crawled below them through wetlands and stone. And maybe that is why Prototaxites continues to fascinate both scientists and ordinary people alike. Not simply because it was large or ancient or difficult to classify, but because it forces a deeper realization about Earth's past. The planet was not always moving predictably toward the ecosystems we recognize today. There were moments when evolution explored paths so unfamiliar that even now we struggle to understand what we are looking at. Prototaxites stands at the edge of that forgotten world, like a shadow from a different version of Earth itself. A reminder that before forests ruled the land, before dinosaurs, before mammals, and unimaginably long before human civilization, giant, mysterious organisms once rose alone across silent continents. And even today, we still cannot say with complete confidence what they truly were. Long before forests covered the continents in endless green, before leaves whispered through branches, before birds nested above the ground, or animals moved beneath towering canopies, Earth's land masses existed in a state that would feel deeply unsettling to modern eyes. The world was not empty exactly, but it was unfinished. Vast stretches of exposed rock and wet mineral soil stretched beneath a hazy sky with almost no vertical life at all. If you traveled across those prehistoric landscapes more than 400 million years ago, you would not find ancient woods waiting beyond the horizon. You would not see flowers, grass, or even true trees. Instead, the continents resembled raw terrain abandoned midway through creation itself, quiet except for wind, rain, and the slow, invisible work of microscopic organisms trying to transform barren stone into something capable of supporting larger life. And in that strange transitional world, fungi may have become some of the most important organisms Earth had ever produced. Today, forests feel permanent. It is difficult to imagine a planet without them, because modern ecosystems depend so heavily on trees that they shape climate, soil, rivers, weather patterns, and even the chemistry of the atmosphere itself. Forests regulate temperatures, hold water in the ground, create oxygen, and support countless species. Human civilization evolved beneath their shadow so completely that trees almost feel like a natural default state for land. But for most of Earth's history, forests did not exist at all. The first complex forests only began appearing during the Devonian period, and even then they emerged slowly, unevenly, almost experimentally. Before that transformation, the continents belonged to something entirely different. Early terrestrial landscapes were dominated by low, primitive vegetation, hugging damp surfaces close to rivers and wetlands. Some of the first land plants resembled tiny branching stems rather than modern greenery. Many lacked deep roots, strong vascular systems, or protective structures against drying sunlight. They survived close to moisture because moving inland remained incredibly difficult. The land itself was hostile. Without thick soils to retain nutrients and water, large portions of the continents remained biologically unstable. Rain could wash minerals away easily. Temperatures fluctuated harshly. Ultraviolet radiation struck exposed surfaces more intensely than today. Life had spent billions of years evolving safely within oceans, but the move onto land required entirely new survival strategies. And strangely enough, fungi may have been among the first organisms truly capable of transforming those hostile environments into living ecosystems. Even modern fungi possess abilities that sound almost impossible when examined closely. Certain species can dissolve rock chemically, extracting minerals directly from stone. Others survive in extreme environments, ranging from frozen Antarctic valleys to radioactive ruins near Chernobyl. Underground fungal networks can stretch astonishing distances through soil, quietly transporting nutrients between plants and influencing entire ecosystems without ever becoming visible above the surface. In many ways, fungi specialize in environments where ordinary life struggles. That capability may explain why they became so significant during Earth's earliest terrestrial ecosystems. Hundreds of millions of years ago, before forests stabilized the continents, fungi were already helping reshape the planet itself. Some researchers believe fungal organisms played a major role in breaking down rock into the first true soils. This process sounds simple at first, but it may have changed Earth permanently. Bare rock alone cannot support complex terrestrial ecosystems. Soil acts as the foundation for nearly all life on land, storing nutrients, retaining water, and allowing roots to spread. But soil does not simply appear naturally. It must be created slowly, through weathering, chemistry, and biological activity. Ancient fungi may have accelerated that transformation enormously by secreting acids into rock surfaces and helping decompose early organic material. In a sense, they may have functioned like Earth's first ecosystem engineers, preparing the continents for the rise of forests long before forests existed. That possibility changes the emotional picture of prehistoric Earth completely. Instead of imagining fungi as secondary organisms living beneath ecosystems, they become architects, helping construct terrestrial life from the ground upward. And perhaps that role explains why organisms like Prototaxites could thrive in such extraordinary ways. In the modern world, fungi usually remain hidden because forests dominate surface environments. Trees absorb most sunlight. Roots stabilize soil deeply. Plant ecosystems control landscapes visually and biologically. But before forests emerged, entirely different ecological opportunities existed. There was little competition for vertical space. The tallest plants often remained less than a meter high. Open wetlands stretched across large areas beneath humid atmospheric conditions. Carbon dioxide concentrations were significantly higher than today, creating warm, greenhouse climates in many regions. In those environments, gigantic fungal structures, rising several meters above the ground, may not have been biologically unreasonable at all. They may have occupied ecological niches that vanished permanently once forests evolved. Imagine standing within one of those ancient landscapes at dawn. The air would feel thick with moisture. Mist drifted across dark wetlands, while primitive plants clustered low against the ground. Instead of towering trees overhead, the horizon remained strangely open, interrupted only by isolated columns of Prototaxites, rising through the fog like silent monuments. No birds crossed the sky, because birds would not exist for hundreds of millions of years. No mammals moved through underbrush, because mammals had not evolved yet either. Even insects remained primitive. The silence itself would feel unfamiliar. Modern forests are alive with constant movement and sound, but early terrestrial Earth may have felt eerily still, as though the planet were only beginning to experiment with complex life on land. And perhaps that atmosphere explains why this period feels so haunting when reconstructed scientifically. It represents a version of Earth balanced between worlds. Oceans had already hosted life for billions of years, yet the continents remained biologically incomplete. Evolution was still testing possibilities. Entire forms of life emerged briefly before disappearing forever. Ecosystems had not stabilized into familiar modern patterns yet. There were no ancient forests stretching endlessly across continents, because trees themselves were evolutionary newcomers, still learning how to survive. In fact, some of the earliest tree-like plants faced enormous biological limitations. Moving water upward through vertical structures is surprisingly difficult. Modern trees rely on sophisticated vascular systems evolved over immense timescales. Early plants lacked many of those adaptations. Some collapsed under their own weight if they grew too tall. Others depended heavily on wet environments because they could not retain moisture effectively. Forests did not suddenly appear overnight. They emerged gradually through millions of years of evolutionary experimentation. During that long transition, fungi may have occupied ecological positions later taken over by plants. And there is another possibility, even more fascinating to consider. Some scientists suspect fungi and early plants may have evolved together through deep biological partnerships. Even today, most plants depend heavily on fungal relationships underground. Fungal networks attach to roots and help plants absorb nutrients more efficiently. In exchange, plants provide sugars produced through photosynthesis. This relationship, called mycorrhizal symbiosis, is so widespread that many modern ecosystems could barely function without it. Some researchers believe these partnerships may date back to the earliest colonization of land itself. In other words, plants may never have conquered the continents alone. Fungi may have helped guide them onto land from the very beginning. That idea quietly reshapes how we think about Earth's history. Forests are often imagined as triumphs of plant evolution. But beneath every forest today exists a hidden fungal infrastructure connecting roots through dark underground networks. The relationship between plants and fungi is ancient beyond imagination. Older than dinosaurs, older than vertebrates walking on land, perhaps even older than forests themselves. In some ways, fungi never stopped shaping terrestrial life. They simply became less visible after trees rose to dominate the surface world. Yet, during the age before forests, their influence may have been impossible to ignore. Some paleontologists even argue that early terrestrial ecosystems should not be imagined primarily as primitive forests at all. Instead, they may have resembled vast fungal plant mosaics spread across humid landscapes unlike any modern environment. Wet microbial soils, mats of simple vegetation, towering Prototaxites structures, shallow waterways, and primitive arthropods together formed ecosystems operating according to ecological rules now largely extinct. This is important because human beings naturally interpret Earth's past through modern analogies. We imagine ancient jungles, ancient swamps, ancient deserts, resembling familiar environments. But much of early terrestrial Earth may have felt more alien than ancient. The farther back scientists look, the more evolution appears experimental rather than predictable. Entire ecosystems existed before modern categories fully separated into recognizable forms. Fungi, plants, algae, and microbial systems may have overlapped in ways difficult to classify cleanly today. And that uncertainty gives this prehistoric world much of its power. Because the age before forests was not simply a primitive version of modern Earth waiting for trees to arrive, it was its own world entirely. A planet where the land itself remained biologically unstable, where giant fungal towers may have stood as the tallest organisms on Earth, and where life was still inventing the systems that would eventually support everything familiar to us now. Looking backward into that distant landscape feels almost like staring into another planet, hidden beneath Earth's own history. And perhaps the strangest realization of all is this: the modern world still rests upon foundations built during that forgotten age. Every forest today grows from soil systems shaped partly by ancient fungi. Every terrestrial ecosystem depends on biological relationships first established during those unstable prehistoric experiments. Even now, beneath modern forests, fungal networks continue moving nutrients silently through darkness, just as their ancestors may have done hundreds of millions of years ago. The giants, like Prototaxites, disappeared long ago, but the deeper fungal influence on Earth never vanished. It simply retreated underground, becoming invisible while quietly continuing to hold entire ecosystems together beneath our feet. There may have been a time in Earth's history when the continents looked less like ancient wilderness and more like the surface of another planet entirely. Not because the land was lifeless, but because the life covering it followed patterns so unfamiliar that the modern mind struggles to process them naturally. More than 400 million years ago, before forests rose across the continents and long before animals ruled the land, Earth may have entered an age where giant fungal towers stood above nearly everything else alive. Imagine walking across those prehistoric landscapes beneath a dim, humid sky. The ground is dark and uneven, covered in primitive vegetation no taller than your knees. Thin, branching plants spread close to shallow wetlands, while sheets of mist drift across open terrain. Rain falls often here, sometimes for weeks without stopping, feeding an atmosphere thick with moisture and carbon dioxide. There are no leaves overhead to block the sky, because trees do not exist yet. No deep forests absorb sound. No birds move through branches. The silence feels endless. And then, emerging from the fog in the distance, enormous pillars rise from the earth, like the ruins of forgotten monuments. Some stand alone. Others appear in scattered clusters, stretching across the landscape. Tall, cylindrical, strange. Prototaxites. If current interpretations are correct, these fungal giants may have dominated portions of the Devonian world for millions of years. In many regions, they were likely the tallest structures visible across entire ecosystems. That idea alone changes the emotional atmosphere of prehistoric Earth completely. Modern people instinctively associate large vertical forms with trees because forests define terrestrial landscapes today. But during this distant chapter of Earth's history, forests had not yet conquered the continents. The planet's surface remained comparatively open, unstable, and biologically experimental. In that environment, giant fungal organisms could rise without serious competition from woody plants. Some paleontologists suspect these towering structures may have appeared almost surreal against the otherwise low prehistoric vegetation. From far away, they might have resembled massive weathered columns standing motionless in endless wetlands. And unlike trees, they would not have formed dense shaded canopies. Instead, they may have stood separated across the terrain, allowing pale light to spill between them through drifting fog and constant rain. What makes this world so fascinating is not only how alien it appears, but how scientifically plausible it may actually have been. The Devonian atmosphere created conditions dramatically different from modern Earth. Carbon dioxide concentrations remained extremely high compared to today, helping produce warmer global temperatures and extensive humid environments. Oxygen levels fluctuated throughout the period, sometimes increasing significantly as terrestrial ecosystems expanded. Meanwhile, the continents themselves were still changing rapidly. River systems spread nutrients across primitive soils, while microbial activity transformed bare rock into increasingly complex terrestrial environments. These unstable ecosystems created ecological opportunities that no longer exist in the modern world. Giant fungi may have flourished precisely because Earth had not yet settled into the biological balance we now recognize. In a sense, the planet was still deciding what terrestrial life would become. And perhaps that is why this lost world feels so haunting. Evolution had not narrowed its possibilities yet. The familiar hierarchy of forests, animals, and flowering plants had not fully emerged. Instead, Earth hosted ecosystems balanced around organisms and relationships now mostly forgotten. The continents belonged to pioneers, strange life forms experimenting with survival strategies during one of the most important transitions in planetary history. Prototaxites may have represented one of evolution's boldest experiments. Some fossil evidence suggests these organisms survived across vast spans of time and geography. Their remains have been discovered in regions that once belonged to ancient landmasses scattered across prehistoric Earth. This distribution hints that they were not isolated curiosities confined to one ecosystem. They may have been widespread features of entire continents. In certain landscapes, fungal towers could have shaped the visual identity of the planet itself. Imagine storms rolling across open Devonian plains, while dark vertical structures emerge through curtains of rain. Imagine dawn sunlight breaking weakly through thick atmospheric haze, illuminating columns covered in moisture, while primitive arthropods crawl across the wet ground below. It is difficult not to notice how cinematic this world begins to feel when reconstructed carefully. Yet, beneath that visual strangeness lies something even more profound. These fungal giants existed during a moment when life on land remained deeply fragile. Today, forests stabilize ecosystems automatically. Tree roots hold soil in place. Complex food webs support enormous biodiversity. But early terrestrial environments lacked much of that stability. Floods could reshape landscapes quickly. Soil systems remained shallow and inconsistent. Nutrient cycles were still developing. In many ways, the continents themselves behaved almost like newly formed biological territory waiting to be colonized fully. Organisms capable of surviving there needed remarkable adaptability. Fungi possessed exactly those kinds of advantages. Even modern fungi excel in unstable environments because they can absorb nutrients externally, spread through microscopic networks, and tolerate conditions many organisms cannot survive. During the Devonian, those traits may have allowed giant fungal systems to dominate spaces where more complex plant ecosystems had not yet succeeded. Some scientists suspect Prototaxites may have anchored itself through extensive underground structures spreading beneath the soil surface. If true, the visible towers might have represented only a fraction of the organism itself. Much like modern fungi today, the largest portions could have remained hidden underground, silently processing nutrients across wide areas while vertical structures rose above the surface. That possibility changes how these giants should be imagined. Rather than isolated towers, they may have functioned as parts of enormous interconnected biological systems stretching beneath prehistoric landscapes. Entire fungal networks may have linked wetland ecosystems together long before forests established root systems of their own. And perhaps the most unsettling realization comes when considering scale. Humans are accustomed to forests filled with movement and sound. Animals rustle through undergrowth. Wind shakes branches overhead. Ecosystems pulse constantly with visible life. But the world of giant fungal towers may have felt profoundly still. Most terrestrial animals had not evolved yet. There were no reptiles, no mammals, no birds. The dominant creatures on land were primitive arthropods, early relatives of centipedes, millipedes, arachnids, and insects. Some crawled slowly across wet surfaces, feeding on decaying material or microbial growth. Others hunted smaller organisms through dark wetlands beneath towering fungal structures. The atmosphere likely carried dense, earthy smells from constant moisture and decomposition. Spores may have drifted invisibly through the air in enormous quantities. During storms, rainwater could have poured down the sides of fungal towers while rivers spread across primitive floodplains beneath them. In some regions, lightning may have illuminated entire fungal landscapes at night without a single tree visible against the horizon. It is difficult to overstate how different this world truly was from anything alive today. Even modern rainforests, ancient as they feel, are products of ecosystems that evolved much later. the Devonian world belonged to earlier biological experiments entirely. And perhaps that explains why Prototaxites continues capturing scientific imagination so powerfully. It represents more than an unusual fossil. It represents a glimpse into a version of Earth where evolution briefly explored a radically different path for terrestrial dominance. In the modern world, fungi survive mostly in hidden ecological roles beneath plants and animals. But during this forgotten age, they may have occupied the top of terrestrial ecosystems themselves. Some researchers even wonder whether landscapes dominated by giant fungi may have influenced the evolution of early terrestrial organisms in ways still poorly understood. Primitive arthropods navigating among towering fungal structures would have experienced a world physically and chemically unlike modern forests. The earliest soil ecosystems formed beneath these strange conditions. Entire nutrient cycles developed around organisms that no longer dominate surface environments today. In many ways, the rise of forests may have erased evidence of earlier ecological systems almost completely. Once true trees evolved stronger vascular tissues and deeper root systems, they gradually transformed the continents. Forests spread. Soil stabilized further. Shade increased. Ecological competition intensified. The age of giant fungal towers slowly faded into deep time beneath the expansion of plant-dominated ecosystems. Yet traces of that forgotten world remain hidden inside stone. Fossils preserved across ancient rocks continue revealing fragments of landscapes almost impossible to imagine fully. And the more scientists investigate them, the stranger the story becomes. Because the existence of Prototaxites suggests Earth's ecosystems were once far more flexible than modern biology often assumes. Entire worlds may have flourished under ecological rules now completely extinct. Looking backward into the Devonian is not like looking at an earlier version of our world. It is more like looking at an alternate Earth buried beneath the present one. A humid planet of fog-covered plains, primitive wetlands, silent horizons, and towering fungal structures rising through ancient storms long before forests claimed the land. And somewhere within that alien silence, evolution was slowly preparing the foundations for every terrestrial ecosystem that would eventually follow, including our own. When people imagine forces powerful enough to reshape Earth's climate, they usually think about volcanoes darkening the sky, asteroid impacts ending entire eras, or shifting oceans changing the balance of heat across the planet. Very few imagine fungi. Quiet organisms hidden beneath forest floors do not seem capable of altering the atmosphere of an entire world. And yet, hundreds of millions of years ago, long before humans existed, and long before forests covered the continents, fungi may have helped trigger environmental transformations so enormous that they permanently changed the direction of life on Earth itself. The strange part is that they may have done it slowly, almost invisibly, through processes that seemed insignificant at first. A thin layer of organic decay here, a microscopic chemical reaction there, networks spreading silently through wet, prehistoric soils. But over immense spans of time, tiny biological actions accumulate into planetary consequences. And in the Devonian world, fungi may have become one of the most influential hidden forces the Earth had ever known. To understand how this could happen, it helps to imagine just how different the atmosphere was during that ancient era. More than 400 million years ago, carbon dioxide levels were dramatically higher than today. The planet was warmer overall, with greenhouse conditions shaping much of the climate. Rainfall patterns were intense in many regions, especially across expanding wetlands and low continental plains. The land itself remained biologically unstable. Large forests, capable of storing carbon efficiently, had not fully evolved yet, and soils were still shallow across huge portions of the continents. Earth was in the middle of a slow transition from a mostly barren terrestrial world into a planet increasingly dominated by complex ecosystems on land. And hidden inside that transition was a problem evolution needed to solve. Life moving onto land required nutrients. Plants needed minerals. Soil needed structure. Ecosystems needed ways to recycle dead organic material efficiently. Without those systems, terrestrial life could never expand beyond isolated patches near water. Fungi may have become the organisms that solved that problem first. Even modern fungi perform a role so essential that forests would collapse without them. They break down dead material and return nutrients to ecosystems. Fallen wood, dead roots, leaves, and decaying organisms are all recycled through fungal decomposition. Without fungi, forests would slowly drown beneath layers of undecomposed material. But during the Devonian period, this process may have carried even greater importance, because terrestrial ecosystems were still primitive and fragile. Nutrients were difficult to retain. Soil systems were underdeveloped. Organic matter needed to be broken down rapidly enough to support expanding life on land. Ancient fungi may have accelerated that cycle dramatically, and, as they spread across the continents, they likely began influencing the atmosphere itself. One of the most important connections involves carbon. Earth's climate is deeply tied to the movement of carbon through the atmosphere, oceans, rocks, and living organisms. Plants absorb carbon dioxide through photosynthesis. Animals release carbon back into the environment. Geological processes store or release carbon over immense timescales. Fungi participate in that cycle by breaking down organic matter and redistributing nutrients through ecosystems. Today, this happens continuously beneath forests all over the world, mostly unnoticed. But during Earth's early terrestrial history, fungal activity may have contributed to much larger climate shifts because ecosystems were still changing rapidly and atmospheric carbon dioxide remained extremely high. Some scientists suspect the expansion of terrestrial life during the Devonian gradually reduced atmospheric carbon dioxide enough to cool parts of the planet over long timescales. Fungi may have played a major supporting role in that transformation. They helped create soils capable of supporting larger plant ecosystems. They accelerated decomposition cycles. They interacted directly with early plant life through underground partnerships. In many ways, fungi may have acted like invisible engineers, preparing the continents for forests long before forests became dominant. And once larger plant ecosystems expanded, they began drawing enormous amounts of carbon dioxide from the atmosphere through photosynthesis. That process may have contributed to long-term climate cooling during later Devonian periods. In other words, fungi may not have altered the climate alone, but they could have helped create the ecological systems that made planetary climate shifts possible. That idea becomes even more fascinating when considering the relationship between fungi and early plants. Today, most plants rely on fungal partnerships beneath the soil called mycorrhizal networks. Fungi connect directly to plant roots, extending microscopic filaments outward through soil and helping absorb nutrients and water more efficiently. In exchange, plants provide sugars produced through sunlight. It is one of the oldest and most widespread biological partnerships on Earth. Some researchers believe this relationship was essential from the very beginning of terrestrial plant evolution. Early plants moving onto land faced brutal environmental stress. Nutrients were scarce. Soil barely existed. Water retention was poor. Without fungal assistance, those primitive plants may have struggled to survive far from wetlands and shallow waterways. Fungi may have effectively guided plant life across the continents, helping terrestrial ecosystems spread outward into increasingly complex environments. That partnership may sound almost peaceful at first, but its planetary consequences were enormous. As plants expanded, they altered weather patterns, stabilized soils, increased oxygen production, and changed atmospheric chemistry. Forests eventually transformed the climate systems of Earth permanently. Yet beneath those forests, fungi remained intertwined with the process at every stage. They were never passive background organisms. They were participants in shaping the entire terrestrial biosphere. And perhaps that is why the Devonian world feels so different when viewed carefully. It was not simply a world waiting for forests to arrive. It was a planet undergoing biological reconstruction from the ground upward. Every new ecosystem changed the atmosphere slightly. Every fungal network spreading through primitive soils altered nutrient cycles. Every expansion of plant life influenced carbon storage, erosion, and climate patterns. Earth was becoming something new. Some scientists even suspect fungal weathering may have accelerated chemical reactions capable of drawing carbon dioxide out of the atmosphere through rock breakdown. This process is surprisingly important in Earth's climate system. When certain rocks weather chemically, carbon becomes trapped over long periods rather than remaining in the atmosphere as greenhouse gas. Fungi are remarkably effective at breaking down rock surfaces using organic acids and microscopic penetration. During the Devonian, widespread fungal activity across expanding land ecosystems may have increased weathering rates substantially. Over millions of years, even slow changes like this can reshape atmospheric chemistry on a planetary scale. The idea is both subtle and astonishing. Tiny fungal organisms spreading through prehistoric landscapes may have contributed to long-term climate changes affecting the entire future of terrestrial life. Yet, the deeper scientists investigate these ancient systems, the more complicated the story becomes. Climate shifts during the Devonian likely involved many interacting forces simultaneously. expanding forests, tectonic activity, ocean chemistry, volcanic processes, and atmospheric feedback loops all influenced one another across immense timescales. Fungi were likely part of a larger ecological transformation rather than a single dominant cause. But that complexity may actually make the story more compelling, not less. Earth's history is rarely shaped by isolated events alone. Instead, the planet changes through interconnected systems, quietly influencing one another over millions of years. And fungi appear again and again within those hidden connections. There is also something strangely poetic about the possibility that organisms associated today with decay may once have helped build the foundations of modern terrestrial life. Fungi recycle death into growth. They break apart dead material and return it to ecosystems. In a sense, they transform endings into beginnings constantly. During the Devonian, that ability may have helped ecosystems stabilize enough for forests to emerge. Without efficient nutrient recycling, terrestrial ecosystems could not expand sustainably. The rise of forests may have depended partly on ancient fungal systems already operating beneath the surface. And once forests spread across the continents, Earth itself began changing more rapidly than ever before. Oxygen levels increased, carbon dioxide declined. Animal life expanded into new ecological opportunities. Rivers changed shape because roots stabilized soils differently. Weather patterns evolved as forests altered moisture cycles. Entire climate systems shifted. Looking backward through deep time, it becomes increasingly difficult to separate fungi from the larger transformation itself. They were not standing outside the process. They were woven into it from the beginning. And perhaps the strangest realization of all is that this hidden influence never truly ended. Even now, modern climate systems remain deeply tied to fungal ecosystems beneath forests worldwide. Carbon storage in soils depends heavily on fungal activity. Nutrient cycles continue flowing through underground fungal networks. Entire forests still communicate chemically through mycorrhizal systems beneath the surface. The ancient relationship between fungi, plants, soil, and climate did not disappear after the Devonian. It simply became less visible as forests took over the world above ground. Yet, underneath every modern forest floor, traces of that ancient planetary partnership still survive. Silent fungal networks continue shaping ecosystems much the same way their distant ancestors may have done hundreds of millions of years ago, back when giant fungal towers stood across prehistoric continents and Earth's climate itself was still being rewritten by organisms no human would ever witness. If a human being could somehow step into the world of giant fungal towers hundreds of millions of years ago, the first feeling would probably not be fear. It would be confusion. The landscape would feel wrong in ways difficult to explain immediately. The sky would seem wider without forests. The ground would appear strangely unfinished, covered in low, primitive vegetation and dark, wet soil stretching across endless plains. Towering fungal structures would rise through drifting fog like silent monuments. But the true strangeness of that world would reveal itself slowly, movement by movement, as unfamiliar creatures emerged from beneath the shadows of those ancient towers. Because the age of Prototaxites was not empty, it was inhabited by organisms so bizarre that many seem almost invented when viewed through modern eyes. Some crawled like insects but reached impossible sizes. Others resembled sea creatures stranded permanently on land. Entire branches of life flourished during this period, only to vanish so completely that they left no obvious descendants behind. This was not yet the age of reptiles, mammals, or dinosaurs. It was an earlier and stranger kingdom of life entirely. One dominated largely by arthropods, creatures built with external skeletons, segmented bodies, and ancient survival strategies carried over from Earth's oceans onto land. During the Devonian period, vertebrate animals were only beginning to experiment with terrestrial existence. Fish still ruled the waters. Amphibian-like creatures had not yet diversified widely across the continents. But arthropods were already moving through the prehistoric wetlands beneath giant fungal towers, exploring ecological opportunities that almost no larger animals existed to challenge. And because terrestrial ecosystems were still developing, some of these organisms evolved into forms that seem almost surreal today. Among the strangest were the giant millipede relatives known as Arthropleura. Although some species appeared later than the peak age of Prototaxites, they represent the type of bizarre terrestrial arthropod ecosystems that emerged during these ancient periods. Some Arthropleura individuals may have exceeded 2 meters in length, making them among the largest land invertebrates ever known. Imagine a creature resembling a gigantic armored centipede, slowly moving through wet, prehistoric terrain beneath fungal towers taller than houses. No birds hunted it from above. No mammals chased it through forests. Entire predator-prey systems familiar to modern life had not evolved yet. In many ways, these giant arthropods occupied ecological spaces that later disappeared completely once vertebrate animals diversified across the land. And Arthropleura was not alone. Ancient scorpion relatives also explored terrestrial environments during these eras. Some early scorpions retained strong ties to aquatic habitats, while others adapted increasingly to land. Their appearance would have looked disturbingly familiar even hundreds of millions of years ago. Long, segmented tails, armored bodies, clawed limbs, moving silently through wetlands beneath drifting mist. Certain species reached sizes far larger than most modern scorpions. Combined with the strange fungal landscapes around them, these creatures would have transformed Devonian ecosystems into scenes almost impossible to compare directly with the modern world. Yet perhaps even stranger were the giant aquatic arthropods lurking nearby in rivers, swamps, and shallow seas connected to these fungal-covered continents. The Eurypterids, often called sea scorpions, were among the most formidable predators of their time. Some species grew over 2 meters long and possessed powerful grasping limbs capable of capturing prey in murky waters. Although most remained aquatic, their presence shaped the atmosphere of the Devonian world deeply. Wetlands beneath giant fungal towers were not isolated from surrounding aquatic ecosystems. Rivers, floodplains, shallow coastal waters, and swamps blended together across enormous prehistoric landscapes. In many regions, the boundary between land and water remained fluid and unstable. Primitive terrestrial ecosystems existed alongside ancient aquatic predator kingdoms, still dominating much of the planet. And perhaps that transitional instability is what made these ecosystems feel so alien. Earth had not fully committed to life on land yet. The continents remained experimental territory where marine lineages, primitive plants, fungal systems, and arthropods interacted in combinations with no modern equivalent. Some organisms still depended heavily on moisture because fully terrestrial adaptations remained incomplete. Others may have spent portions of their life cycles between water and land. Entire ecosystems operated under evolutionary rules still being invented in real time. The result was a world that lacked the ecological familiarity modern humans unconsciously expect. There were no birds filling the air with sound, no grazing mammals reshaping landscapes, no flowering plants coloring the terrain. Instead, the dominant motion came from crawling organisms moving slowly across wet soils beneath towering fungal structures, releasing spores into humid air. And one reason many of these ancient arthropods achieved such enormous sizes may have involved the atmosphere itself. During parts of the Paleozoic era, oxygen levels appear to have risen significantly higher than modern concentrations. Scientists still debate the exact timing and fluctuations, but elevated oxygen may have allowed certain arthropods to grow much larger than their modern relatives. Arthropods breathe differently from mammals. Instead of lungs, many rely on passive respiratory systems where oxygen diffuses directly into their bodies through small openings. Higher atmospheric oxygen could support larger body sizes more effectively under those conditions. In today's atmosphere, giant dragonflies or meter-long arthropods would struggle physiologically. But in the oxygen-rich worlds developing later in the Paleozoic, evolution briefly allowed gigantic invertebrates to flourish. This possibility transforms the emotional atmosphere of the fungal world again. Imagine enormous armored arthropods emerging from mist beneath giant fungal towers, while oxygen-rich air thickens ancient wetlands. The environment begins to feel less like Earth's past and more like an entirely different biological reality. Yet despite their strange appearance, these organisms were not evolutionary mistakes. They were highly adapted survivors, thriving within ecosystems perfectly suited to their time. Modern humans often interpret prehistoric life as primitive simply because it came earlier. But evolution does not move toward predetermined goals. The Devonian world was not an incomplete rehearsal for modern ecosystems. It was a functioning planet filled with organisms optimized for conditions radically different from today. Giant arthropods, fungal towers, primitive wetlands, and early terrestrial plants formed interconnected ecosystems capable of surviving for millions of years. Some of these creatures may even have depended directly on fungal systems themselves. Modern arthropods interact constantly with fungi through feeding, decomposition, and ecological relationships. Ancient species likely did the same. Fungal networks recycled nutrients through prehistoric soils, while arthropods fed on decaying organic matter, microbial growth, or each other. In some ways, fungi may have formed the biological foundation supporting entire terrestrial food webs before forests fully developed. And there is another unsettling possibility hidden within these ancient ecosystems. Because terrestrial vertebrates remained relatively limited During much of this era, arthropods may have experienced ecological freedom unlike anything seen later in Earth's history. Once reptiles, amphibians, birds, and mammals diversified, they imposed enormous predatory pressures on invertebrate life. Many giant arthropod forms disappeared over time as vertebrate ecosystems expanded. But during the age of fungal towers, those pressures remained comparatively weak. Arthropods could explore ecological roles later dominated by vertebrates. Some became enormous scavengers, others evolved into major predators. Entire evolutionary experiments unfolded beneath the shadow of Prototaxites before eventually vanishing into extinction. And perhaps that is what makes this ancient world feel so haunting when reconstructed carefully. It represents a biological reality where familiar hierarchies had not formed yet. Today, humans dominate terrestrial ecosystems intellectually and technologically. Mammals dominate large animal niches physically. Forests dominate landscapes visually. But the Devonian world belonged to entirely different rulers. Giant fungi towered above primitive wetlands. Arthropods crawled through ecosystems still under construction. Rivers carried armored predators through shallow waters beside fungal plains. The atmosphere itself behaved differently. Even sunlight filtering through prehistoric haze may have looked unfamiliar due to atmospheric composition and environmental conditions unlike the modern world. Looking backward into that age feels almost like glimpsing Earth before it settled into the version we recognize now. And the deeper scientists investigate these ancient ecosystems, the more evidence suggests they were astonishingly complex, despite appearing primitive at first glance. Soil ecosystems developed rapidly. Nutrient cycles expanded. Organisms interacted through increasingly intricate ecological relationships. Evolution was accelerating. The foundations of future terrestrial life were forming silently beneath fungal towers and drifting spores. Yet many of the creatures participating in that transformation would eventually disappear so completely that modern Earth barely remembers them at all. Fossils preserve fragments, tracks crossing ancient mud, armored exoskeletons buried beneath sediments, impressions left by bodies long dissolved into stone. But the living atmosphere of those ecosystems remains partly unreachable, suspended somewhere between science and imagination. Perhaps that uncertainty is fitting, because the world beneath the fungal towers was never meant for human eyes. It belonged to an earlier Earth, still experimenting with what life on land could become, filled with strange giant creatures moving through wet, prehistoric silence, while towering organisms unlike anything alive today watched over landscapes that no longer exist. For millions of years, the giant fungal towers of the Devonian world may have stood almost uncontested across prehistoric landscapes, rising through mist above low, primitive vegetation, while strange arthropods moved beneath them. They survived changing climates, unstable ecosystems, and a planet still struggling to build life on land. And then, slowly, they disappeared. Not in a sudden catastrophe, not in a single extinction event dramatic enough to leave obvious scars across the fossil record. Instead, they seem to fade gradually from Earth's story, vanishing so completely that by the time forests fully conquered the continents, the age of giant fungal towers was already ending. What makes this disappearance so fascinating is that scientists still cannot explain it with complete certainty. There was no giant asteroid impact tied directly to their decline. No singular volcanic apocalypse clearly connected to their extinction. Instead, Prototaxites appears to have vanished during one of the largest ecological transformations Earth had ever experienced: the rise of forests themselves. And strangely, the very ecosystems fungi may have helped create could also have become the reason their giant forms no longer survived. To understand how this happened, it helps to imagine how rapidly the continents were changing during the late Devonian world. Earlier terrestrial landscapes had remained relatively open. Primitive plants stayed low to the ground. Nutrient cycles were unstable. Soil systems were shallow. But evolution does not remain still for long. Over millions of years, plant life began developing more advanced vascular systems, capable of transporting water efficiently through taller structures. Roots grew deeper and stronger. Woody tissues evolved, allowing plants to support increasing height without collapsing under their own weight. And then, for the first time in Earth's history, true forests began spreading across the continents. This transformation was not merely visual. It altered the entire structure of terrestrial ecosystems. Forests changed wind patterns near the ground. They stabilized soils more deeply. They retained moisture differently. They reshaped river systems and influenced atmospheric chemistry on a planetary scale. The open fungal landscapes of earlier periods slowly gave way to dense, expanding ecosystems filled with vertical competition for sunlight and nutrients. And that change may have created a world where giant fungal towers no longer possessed the same ecological advantages they once did. In the age before forests, Prototaxites may have thrived, partly because there was little competition for height. Rising several meters above primitive vegetation offered enormous advantages in spore dispersal and environmental reach. But once true trees emerged, the continents became crowded with increasingly complex plant ecosystems, growing taller and denser over time. Forest canopies blocked sunlight from reaching the ground. Root systems absorbed nutrients aggressively. Soil chemistry changed as massive amounts of plant material accumulated and decomposed. The ecological balance shifted away from the conditions that once supported giant fungal structures. In a strange way, the rise of forests may have erased the very world giant fungi depended on. Some scientists suspect Prototaxites represented an organism highly specialized for transitional ecosystems, environments too unstable for forests, yet rich enough to support large fungal systems. Once forests matured, those transitional habitats may have shrunk dramatically. And unlike trees, fungi do not generate energy directly from sunlight. They rely on absorbing nutrients from surrounding environments. As terrestrial ecosystems became increasingly dominated by large plants, fungal systems may have been forced into different ecological roles beneath the surface, rather than towering above it. In other words, fungi did not disappear from Earth. Only the giant visible forms may have vanished. the fungal kingdom itself remained deeply successful, retreating underground into the hidden networks modern ecosystems still depend upon today. But there may have been additional pressures shaping the decline of giant fungal towers as well. Climate itself was changing during the Devonian period. As forests expanded and terrestrial ecosystems absorbed greater amounts of carbon dioxide, long-term atmospheric changes may have contributed to global cooling trends in certain regions. Weather patterns shifted, soil structures evolved, wetland systems changed, ecosystems became increasingly complex and interconnected. Organisms adapted to earlier greenhouse environments may have struggled under these new conditions. If Prototaxites depended heavily on warm, humid, open landscapes, even moderate climate shifts over millions of years could have reduced its ecological range significantly. And because fossils preserve only fragments of deep time, scientists may never reconstruct the full sequence of pressures these organisms faced. There is also another possibility researchers occasionally consider, though evidence remains uncertain. The spread of increasingly complex terrestrial animals may have altered fungal ecosystems more than we currently understand. As arthropods diversified and vertebrate life slowly expanded onto land, food webs became more intricate. New grazing behaviors, decomposition patterns, and ecological interactions emerged. Organisms, once protected by environmental simplicity, suddenly existed within ecosystems growing rapidly more competitive and biologically crowded. Giant fungal towers may have struggled not against one single enemy, but against an entire world becoming more complex around them. Evolution often works this way. Extinction is not always violent. Sometimes entire forms of life simply lose their place within changing ecosystems. And perhaps that is why the disappearance of Prototaxites feels strangely melancholic when viewed carefully. These organisms may not have failed because they were weak or poorly adapted. For millions of years, they succeeded remarkably well. Instead, they may have belonged to a world that no longer existed by the end of the Devonian. The open fungal plains faded beneath expanding forests. Primitive wetlands transformed into increasingly stable terrestrial ecosystems. The continents became less alien and more familiar. In a sense, Earth itself moved on from the conditions that once allowed giant fungi to dominate the horizon. Looking at modern forests today, it is easy to forget how revolutionary trees once were. Their rise permanently reshaped the atmosphere, climate, soil systems, and biodiversity of the planet. Forests created ecological opportunities, leading eventually to reptiles, mammals, birds, and ultimately humans. But every major evolutionary success changes the world for earlier life forms too. Some adapt, some shrink into hidden niches, others vanish entirely. Prototaxites may have become one of evolution's forgotten casualties during the rise of the modern terrestrial world. Yet the mystery deepens because scientists still debate exactly what Prototaxites even was. And that uncertainty complicates every extinction theory surrounding it. If these giant structures were truly fungi, their disappearance might reflect ecological competition with forests and changing climates. But if they represented some extinct hybrid form, unlike modern organisms entirely, their decline may involve biological limitations we do not yet understand. Perhaps they relied on atmospheric conditions that no longer existed. Perhaps they reproduced too slowly to compete with rapidly evolving plant ecosystems. Or perhaps they belonged to evolutionary pathways that simply reached dead ends over geological time. The farther back scientists peer into deep time, the more they encounter organisms operating according to ecological rules now extinct. And there is another haunting detail hidden inside the fossil record itself. Prototaxites does not appear to end dramatically. Its fossils simply become rarer, then rarer still, until eventually they disappear from known geological layers altogether. That gradual fading creates an eerie feeling, almost like watching an ancient civilization dissolve into history without leaving behind written records explaining what happened. One era quietly gives way to another. The fungal towers stop appearing. Forests spread wider. The atmosphere changes. New organisms dominate the land. And eventually, Earth forgets the world that existed before trees. Yet, traces remain buried inside stone. Fossils of giant fungal structures continue emerging from ancient rocks, reminding modern scientists that the planet once hosted ecosystems radically different from anything alive now. The disappearance of Prototaxites also reveals something deeper about evolution itself. Modern humans often imagine Earth's history as a steady progression toward increasingly advanced life, almost as though nature were working toward predetermined outcomes. But the story of giant fungal towers suggests something far stranger. Evolution experiments constantly. Entire worlds appear temporarily, flourish for millions of years, then vanish when environmental conditions shift. Success in one age does not guarantee survival in the next. The Devonian world supported organisms that would seem impossible today, because the planet itself operated differently then. As Earth changed, so did the possibilities available to life. And perhaps the most unsettling realization is that no ecosystem, no matter how dominant, remains permanent forever. There was once a time when giant fungal towers stood above the continents as some of the tallest living structures on Earth. If intelligent observers had existed then, they may have assumed those organisms would rule terrestrial landscapes indefinitely. Yet eventually, forests replaced them. Later, dinosaurs would dominate the world for millions of years before disappearing too. Entire biological empires rise and fall across deep time, while Earth continues changing beneath them. In that sense, the extinction of giant fungi becomes more than an isolated prehistoric mystery. It becomes part of a larger pattern woven through the entire history of life on Earth. The quiet truth that even the strangest and most successful worlds eventually fade into silence. For all the decades scientists have spent studying Prototaxites, one unsettling possibility still hangs over the entire mystery like fog across a prehistoric swamp. What if these enormous structures were never truly fungi at all? It sounds strange at first because the image of giant fungal towers has become deeply attached to the story of early Earth. Modern documentaries, scientific illustrations, and paleontological discussions often describe them as giant mushrooms or colossal fungal columns rising above ancient landscapes. Yet, The deeper researchers examined the fossils, the more uncomfortable certainty became. Even now, after microscopic analysis, chemical studies, and generations of debate, no explanation fully solves every piece of the puzzle. And perhaps that uncertainty is more important than the answer itself. Because Prototaxites may represent something even stranger than a giant fungus, it may represent a form of life so ancient and so biologically distant that modern science struggles to classify it, using categories created from the living world around us today. The problem begins with a simple reality about deep time. Fossils do not preserve organisms perfectly. Most ancient life disappears completely after death. Soft tissues decay. Internal chemistry changes. Pressure and heat alter structures over millions of years. Paleontology works with fragments, impressions, mineralized remnants buried beneath unimaginable spans of time. Scientists reconstruct entire ecosystems from scattered clues surviving against enormous odds. And the farther back into Earth's history researchers look, the stranger and more incomplete those clues become. Prototaxites lived during a period when terrestrial ecosystems themselves were still experimental. Evolution had not yet settled into the familiar divisions modern biology depends upon. Entire groups of organisms may have existed in forms unlike anything alive now. That possibility changes the way scientists interpret these fossils. Instead of asking only whether Prototaxites was a fungus, some researchers have started asking a deeper question entirely. What if it belonged to a category of life that no longer exists? The earliest scientists who studied Prototaxites believed it was wood from primitive trees. That interpretation made intuitive sense because the fossils resembled trunks. Some specimens showed ring-like internal patterns similar to growth rings. But over time, the plant theory weakened as closer analysis revealed missing features expected in true wood. There were no recognizable vascular tissues capable of transporting water like modern trees use. The internal organization appeared chaotic compared to plant structures. And, perhaps most importantly, the surrounding fossil environments often predated the rise of large woody trees entirely. Something did not fit. Later researchers proposed algae instead. Giant algae can form large structures, and Earth's early ecosystems remained closely tied to aquatic environments. But this explanation struggled too. The fossils lacked many characteristics expected in marine algae, and the enormous vertical growth seemed difficult to explain in terrestrial settings using algal biology alone. Then came the fungal interpretation, which for many scientists remains the strongest explanation even today. The tangled microscopic tube structures inside Prototaxites resembled fungal filaments called hyphae. Carbon isotope analysis suggested these organisms absorbed nutrients externally rather than producing energy directly through photosynthesis. Their ecological role also fit certain fungal behaviors observed in modern ecosystems. Suddenly, the idea of giant fungal towers dominating prehistoric landscapes no longer sounded impossible. Yet even this theory left behind stubborn, unanswered questions. One major issue involves size and structure. Modern fungi simply do not grow like Prototaxites appears to have grown. Mushrooms today are temporary reproductive structures emerging from much larger underground networks. They are soft, fragile, and short-lived compared to the massive, towering fossils attributed to Prototaxites. Some researchers argue that ancient environmental conditions may have allowed fungi to evolve differently during the Devonian. Others remain unconvinced. Certain fossil structures appear unusually complex or inconsistent with known fungal anatomy. And because no modern equivalent exists, scientists cannot compare Prototaxites directly to living organisms with confidence. It exists in a biological gray zone where similarities overlap without complete agreement. Some paleontologists have explored the possibility that Prototaxites may have been a giant lichen-like organism instead. Lichens are partnerships between fungi and photosynthetic organisms such as algae or cyanobacteria. They behave almost like entirely new life forms created through biological cooperation. Modern lichens can survive in harsh environments where few other organisms thrive, including deserts, frozen mountains, and exposed rock surfaces. During the Devonian, giant lichen-like structures might theoretically have occupied ecological niches similar to those associated with Prototaxites. This idea is fascinating because it transforms the organism from a single species into a biological alliance. Yet, the lichen hypothesis also faces challenges. Modern lichens do not reach anywhere near the enormous scales implied by Prototaxites fossils. And, again, the fossil evidence refuses to fit perfectly into one explanation. The more closely researchers examine the details, the more Prototaxites seems to resist clean classification altogether. And perhaps the strangest possibility of all is that scientists may be trying too hard to force Prototaxites into modern biological categories that did not fully exist yet when it was alive. Today, we separate fungi, plants, algae, and microbial systems into distinct kingdoms because evolution has had hundreds of millions of years to refine those divisions. But during the Devonian world, terrestrial ecosystems remained biologically experimental. Early life on land may have formed partnerships, structures, and ecological strategies unlike anything surviving now. Some scientists quietly suspect Prototaxites may represent one of those extinct experiments, a branch of life that evolved separately before disappearing completely. If true, that possibility changes the emotional meaning of these fossils entirely. They stop being giant versions of familiar organisms and become something much more alien. Not alien in the science fiction sense, but biologically foreign to the modern world itself. A reminder that Earth once hosted forms of life so different that modern science cannot easily describe them anymore. And there is evidence suggesting this may not be impossible. Throughout Earth's history, entire evolutionary lineages have vanished without leaving direct descendants behind. The fossil record preserves countless organisms that fit awkwardly within modern classifications because they belonged to earlier stages of life's experimentation. During periods of rapid evolutionary change, ecosystems often produce bizarre combinations of traits before stable, long-term forms emerge. The Cambrian explosion alone introduced body plans unlike anything alive today. Some ancient organisms appear so strange that paleontologists still debate how they moved, fed, or even which kingdom of life they belonged to. Prototaxites may represent another example of that deep biological ambiguity. Yet, perhaps what makes this mystery so captivating is not merely the uncertainty itself, but what the uncertainty reveals about science. Modern culture often treats scientific knowledge as fixed and complete, as though every mystery eventually resolves into clean certainty. But paleontology rarely works that way. The deeper scientists investigate Earth's ancient past, the more they encounter blurred boundaries and incomplete answers. Prototaxites has been studied for over a century and a half by experts using increasingly advanced technology, yet the organism still refuses to become fully understandable. Its fossils continue offering clues without surrendering the final answer completely. There is something strangely beautiful about that, because it reminds us that Earth's history is larger and stranger than human categories alone can contain. Sometimes, the past does not fit comfortably into modern language. Sometimes, ancient life belongs partly to worlds we no longer have reference points for. Imagine standing within one of those prehistoric fungal landscapes again, watching enormous towers rise through wet Devonian fog beneath a dim, unfamiliar sky. Modern humans instinctively want to label what they are seeing: tree, fungus, plant, lichen. But perhaps those categories themselves would fail in that ancient world. Perhaps Prototaxites existed in an ecological and biological space somewhere between definitions modern biology later separated more cleanly. Evolution does not follow human classification systems. It experiments continuously, creating temporary forms and relationships that may never appear again once conditions change. And perhaps that is why Prototaxites feels so haunting, even now. It stands at the edge of what science can reconstruct confidently from deep time. Not fully understood, not fully classified, suspended somewhere between certainty and mystery. In some ways, the organism has become symbolic of prehistoric Earth itself, a reminder that the ancient planet was not merely an earlier version of the modern world. It was a stranger place entirely, filled with ecosystems and life forms operating according to biological rules that may no longer exist. Even after all our technology, research, and scientific progress, one of the tallest organisms to ever dominate Earth's early continents still remains partially hidden behind millions of years of silence. And maybe that silence is part of the story too, because sometimes the most fascinating truths about Earth's past are not the answers scientists finally reach, but the mysteries that continue surviving despite everything humanity has learned. Imagine for a moment that the world of giant fungal towers never disappeared. Imagine that somewhere in Earth's distant history, the rise of forests slowed, climates shifted differently, and the strange organisms known as Prototaxites continued evolving instead of fading into extinction. The modern world would likely feel almost unrecognizable, not because humans could not survive within it, but because the emotional atmosphere of the planet itself would be completely different. Forests today create a sense of life built upward through branches, leaves, and sunlight. A world dominated by giant fungi would feel darker, wetter, quieter, and somehow more ancient, even if technologically advanced civilizations still emerged within it. The Earth would not resemble a fantasy world exactly. In many ways, it might feel stranger than fantasy because its ecosystems would operate according to biological systems that are scientifically plausible, yet deeply unfamiliar to the modern human mind. To understand how different this alternate Earth could become, it helps to think about what fungi actually are. Modern people often see mushrooms as isolated organisms appearing briefly after rain, but mushrooms are only visible fragments of much larger living systems hidden underground. The true body of a fungus usually exists beneath the surface as vast networks of microscopic filaments spreading through soil, wood, and organic material. Some fungal networks alive today already rank among the largest organisms on Earth. In Oregon, one enormous underground fungus covers several square miles and may be thousands of years old. Most humans living above it would never realize they were walking across a single interconnected organism. Now, imagine if evolution had continued favoring giant, visible fungal structures for hundreds of millions of years, rather than pushing fungi into mostly hidden ecological roles beneath forests. Earth's landscapes might have evolved around towering fungal systems instead of trees. Entire continents could have become covered in dark, spore-filled ecosystems where giant fungal pillars rose through humid air like living architecture. Unlike forests, these fungal landscapes would likely absorb and recycle organic material differently. Soil chemistry could change. Nutrient cycles might operate faster in some environments and slower in others. Massive underground fungal webs could connect ecosystems across extraordinary distances, perhaps creating levels of ecological interdependence even more complex than modern forests. And because fungi interact with decomposition so intimately, the atmosphere of such a world might carry a constant scent of wet earth, organic decay, and moisture-rich soil almost everywhere. The visual appearance of the planet would transform dramatically as well. Modern forests create open, vertical spaces between trunks because trees compete primarily for sunlight above. Giant fungi might evolve entirely different structures, optimized for spore dispersal, moisture retention, or nutrient absorption. Instead of branching canopies filled with leaves, the landscapes might feature enormous column-like growths, broad shelf structures, or towering umbrella-shaped forms releasing clouds of spores into the air. Sunlight reaching the ground could appear dimmer and more diffuse beneath dense fungal haze. Entire regions might remain covered in mist, generated partly by ecosystems retaining massive amounts of moisture. In some climates, giant fungal systems could dominate so heavily that landscapes resemble endless alien wetlands stretching beneath pale skies. And perhaps the strangest consequence involves sound. Modern forests are noisy because they support enormous numbers of birds, insects, and mammals moving constantly through branches and vegetation. But fungal ecosystems might produce quieter environments overall. Thick, humid air absorbs sound differently. Dense fungal structures may not rustle like leaves in the wind. Vast landscapes could feel eerily silent, except for rainfall, distant movement, and the slow dripping of moisture through organic structures larger than buildings. Human beings evolved psychologically within open grasslands, and later among forests filled with familiar biological signals. A fungal world might trigger entirely different emotional responses. The environment could feel simultaneously alive and deeply unsettling. Yet, if giant fungal ecosystems survived long enough, evolution would likely reshape animal life around them too. Modern animals evolved alongside forests, grasslands, and flowering plants. A fungal-dominated Earth might produce creatures adapted for darker, wetter environments, rich in spores and decomposition. Arthropods may have remained larger and more ecologically dominant in certain regions. Some scientists already suspect fungi influenced ancient arthropod ecosystems heavily during the Paleozoic era. If giant fungal systems continued shaping terrestrial environments, entirely different animal lineages might have flourished instead of mammals becoming dominant later. Vertebrate evolution itself could potentially change under those conditions. Large grazing mammals, for example, depend heavily on plant ecosystems like grasslands and forests. A fungal world may not support the same kinds of food chains. Ecosystems might favor scavengers, decomposers, and moisture-adapted organisms instead. And what about humans? That question becomes even more fascinating because fungal ecosystems could influence civilization itself in unexpected ways. Agriculture as we know it depends largely on plant domestication. Human societies evolved around cereals, fruits, vegetables, forests, and grazing animals. But on a fungal Earth, entirely different resources might dominate economies and settlement patterns. Cities could develop around stable, dry regions where giant fungal growth remained manageable. Architecture might evolve to resist moisture, spores, and rapid biological decay. Underground fungal networks could even become integrated into technology or medicine far earlier than in our timeline. Modern science already explores fungal materials for construction, medicine, environmental cleanup, and biological computing systems. On an Earth where fungi remained visibly dominant, humans may have understood fungal biology far more deeply from the beginning of civilization itself. There is also a darker possibility hidden inside this alternate world. Fungi reproduce through spores, and in enormous concentrations, spores can become dangerous, even today. Some modern fungal spores cause respiratory illness, hallucinations, infections, or toxic reactions under certain conditions. In a planet dominated by giant fungal ecosystems, airborne spores could shape human biology and culture profoundly. Entire civilizations might adapt architecturally and genetically to survive constant exposure. Protective breathing systems, filtered living environments, or biologically adapted immune systems could become essential for large populations. In certain climates, wandering unprotected through giant fungal regions might feel as dangerous as crossing deserts or frozen wastelands. And perhaps most unsettling of all, fungal intelligence itself remains poorly understood even in the modern world. Fungi do not possess brains, yet their networks behave in surprisingly complex ways. Some fungal systems distribute nutrients efficiently across enormous distances, respond dynamically to environmental changes, and form intricate cooperative relationships with surrounding organisms. Researchers studying fungal communication sometimes compare underground networks to primitive biological information systems. While there is no scientific evidence that fungi possess consciousness in any human sense, their decentralized intelligence challenges traditional ideas about what complex life should look like. If giant fungal systems continued evolving for hundreds of millions of years, it is difficult to predict how sophisticated those ecological networks might eventually become. Entire forests today already function partly through fungal communication beneath the soil. A fungal-dominated Earth might amplify those relationships into something even stranger. Perhaps ecosystems themselves would behave almost like interconnected superorganisms spanning continents. Of course, much of this remains speculative. Scientists cannot predict alternate evolutionary histories with certainty because small environmental changes can reshape evolution unpredictably over immense timescales. The rise of mammals, flowering plants, dinosaurs, birds, and human beings all depended on countless interconnected events across Earth's history. If giant fungi survived, many other evolutionary pathways would likely change too. Some modern ecosystems might never appear at all. Others could evolve into forms impossible to imagine completely. But that uncertainty is precisely what makes this thought experiment so compelling, because it reveals how fragile and contingent the modern world truly is. Humans often see present-day Earth as natural and inevitable, yet the fossil record suggests otherwise. Entire biological worlds have risen and vanished repeatedly across deep time. Giant fungal towers once stood across prehistoric landscapes because Earth's conditions allowed them to thrive. If history shifted slightly differently, perhaps they would still dominate the continents now. And maybe the strangest realization is this: traces of that fungal world never fully disappeared anyway. Even on modern Earth, fungal networks still shape nearly every terrestrial ecosystem beneath the surface. Forests depend on them. Soil depends on them. Nutrient cycles depend on them. Life on land remains deeply connected to fungal systems that most humans never notice. In some ways, the fungal kingdom never truly surrendered its influence over the planet. It simply became hidden underground, while forests claimed the visible world above. But occasionally, through fossils like Prototaxites, Earth offers glimpses of an older reality, a reminder that our planet once belonged to towering organisms stranger than most science fiction, and under slightly different circumstances, perhaps it still would. Tonight, if you walk into a forest after rain, you are moving through the surviving echoes of a world far older than humanity. Beneath the wet soil under your feet, hidden below roots and fallen leaves, millions of fungal threads are already moving silently through the darkness. They spread through the earth like living veins, connecting trees, recycling death into new life, carrying nutrients across ecosystems that most people never realize are communicating beneath them constantly. Modern science sometimes calls these underground systems the Wood Wide Web, a phrase that sounds almost playful at first, until you understand how ancient and vast these fungal networks truly are. Because long before human civilization, long before dinosaurs, and perhaps Even before forests themselves fully conquered the continents, fungi were already shaping the future of life on Earth. The giant towers of Prototaxites vanished hundreds of millions of years ago, but the deeper fungal influence on the planet never disappeared. It simply became invisible. And maybe that is what makes this story linger in the mind long after the fossils themselves are gone. The world of giant fungal towers feels distant at first, almost unreal, buried so deeply in time that it resembles mythology more than history. Yet pieces of that forgotten earth still surround us now. Every forest depends on fungal systems beneath the surface. Entire ecosystems continue functioning through relationships first established during those ancient Devonian landscapes. The modern world was built partly on biological foundations created during an era most humans have never even heard of. In some ways, the age of giant fungi never truly ended. It only changed form. That realization transforms how modern forests begin to feel when viewed carefully. Trees no longer seem like isolated organisms competing alone for sunlight. Beneath them exists another hidden world, older, darker, and more interconnected. Fungal networks wrap around roots, transporting nutrients and chemical signals between plants. Some studies suggest trees under stress may send warning signals through fungal connections. Young trees sometimes receive nutrients through these underground systems from larger, older neighbors. Dying organisms are broken down and recycled into future growth through fungal decomposition. The forest floor itself behaves less like separate individual organisms and more like a vast biological conversation unfolding beneath human awareness. And perhaps the strangest part is that modern science is only beginning to understand how complex these systems actually are. Researchers continue discovering fungal behaviors that challenge older assumptions about intelligence, cooperation, and ecological organization. Certain fungi can navigate mazes efficiently, adapt dynamically to environmental changes, and build astonishingly resilient underground networks. None of this means fungi are conscious in a human sense, but it does reveal something profound about life on Earth. Intelligence and complexity do not always look the way humans expect them to look. Sometimes they exist quietly beneath the soil, operating across timescales and structures almost invisible to ordinary perception. And when viewed through that lens, the ancient world of giant fungal towers feels less disconnected from modern Earth than it first appears. Prototaxites may have vanished, but the fungal kingdom itself remains one of the most successful forms of life on the planet. It survived every mass extinction event Earth has endured. It adapted through changing atmospheres, collapsing ecosystems, asteroid impacts, ice ages, and the rise and fall of dominant species across hundreds of millions of years. Dinosaurs disappeared. Entire oceans changed chemistry. Continents drifted across the globe. Yet fungi persisted through all of it, quietly reshaping ecosystems again and again. In some ways, the fungal kingdom represents one of the deepest continuous threads connecting Earth's ancient past to the modern world. And perhaps that continuity explains why the story of Prototaxites feels so emotionally powerful despite the enormous distances involved. It reminds us that prehistoric Earth was not merely a primitive version of the present. It was filled with ecosystems operating according to unfamiliar rules, dominated by organisms modern humans barely understand even now. Giant fungal towers rising through prehistoric fog sound almost impossible because they force us to confront how radically different life once was. But they also reveal something equally important. The modern world itself is not permanent either. Forests feel eternal because humans evolved within them. Mammals feel dominant because humanity belongs to that lineage. Yet deep time tells a different story. Earth changes constantly. Entire biological empires rise and vanish. Conditions shift. Ecosystems transform. What seems impossible in one age becomes ordinary in another. The world of giant fungi disappeared because Earth itself changed beneath it. And one day, the modern world will change too. There is something strangely humbling about that realization. Human civilization often behaves as though the planet exists primarily as a stage for our history. Yet humanity occupies only a microscopic fraction of Earth's timeline. Long before the first human looked at the stars and wondered about existence, giant fungal structures may already have towered above silent continents beneath unfamiliar skies. Entire ecosystems flourished and vanished before mammals even evolved. The fossil record preserves countless worlds that once seemed permanent to the organisms living inside them. Looking backward into deep time strips away the illusion that modern Earth represents some final, stable version of the planet. Instead, it reveals a world constantly reinventing itself through evolution, extinction, and ecological transformation. Yet, despite all the mystery surrounding Prototaxites, perhaps its greatest legacy is not scientific uncertainty, but perspective. Because the organism forces modern humans to recognize how little of Earth's history truly belongs to us. Most people can name dinosaurs because dinosaur imagery dominates culture and imagination. But the age of giant fungal towers existed unimaginably earlier, during a chapter of planetary history so distant that even the continents themselves looked unfamiliar. Earth spent millions of years experimenting with ecosystems stranger than most science fiction, long before humanity arrived to observe any of it. And hidden beneath modern forests, traces of those experiments still remain alive today. Every fungal network beneath the soil carries echoes of that ancient world. Every mushroom emerging quietly after rain belongs to a lineage older than trees. The forest floor itself becomes more mysterious once you realize that beneath every step lies an ancient biological system connected to Earth's deepest history. Some scientists even speculate that fungi may become increasingly important to humanity's future as well. Modern research explores fungal materials for sustainable construction, biodegradable packaging, environmental cleanup, medicine, and even biological computing systems. Certain fungi can break down oil spills, digest plastics under specific conditions, and survive in extreme environments hostile to most life. The fungal kingdom continues revealing unexpected capabilities the deeper researchers investigate it. In an odd way, humanity may still be learning from organisms whose ancestors once dominated the prehistoric world before forests existed. And that connection between ancient Earth and the modern future creates a beautiful symmetry within the story. The giant fungal towers vanished, but their descendants remain woven through nearly every ecosystem on the planet, still shaping life quietly from below. Sometimes, the most influential forces in Earth's history are not the loudest or most visible ones. Fungi rarely dominate human imagination because they work in silence. They grow underground. They decompose what has died. They connect roots invisibly through darkness. Yet without them, forests struggle. Soil collapses. Nutrient cycles break apart. Entire ecosystems lose the hidden systems holding them together. In that sense, fungi may represent one of the clearest examples of how life's deepest foundations often remain unseen. And perhaps that is the final emotional truth hidden inside the story of Prototaxites. The giant towers themselves disappeared long ago, erased by time and changing ecosystems, but the quiet biological forces they represented never vanished. They still exist beneath forests, beneath wetlands, beneath the soil of nearly every continent on Earth. Invisible, ancient, patient. The descendants of a kingdom that once may have ruled the horizons of a prehistoric world, before trees, before animals, before human memory itself. And somewhere tonight, beneath dark forests moving softly in the rain, those ancient fungal networks continue spreading silently through the earth exactly as their ancestors once did, hundreds of millions of years ago, carrying forward the last living traces of a lost world almost no one remembers. Thanks for spending this time exploring Earth's lost ancient world with me tonight. If you enjoyed the journey, don't forget to subscribe to Sleepy Earth channel and leave a comment telling me what mysterious topic you'd like to explore next. Wishing you a peaceful night, good luck, and I'll see you in the next adventure.